once we've gathered enough speed around Gargantua, we use Lander 1 and Ranger 2 as rocket boosters to push us out of the black holes of gravity. Imagine light leaving the first stars and galaxies nearly 13.6 billion years ago and traveling through space and time to reach us. Music. Imagine a fundamental theory in physics that provides a description of the physical properties of nature and the scale of atoms and subatomic particles. It is astonishing to think how modern physics of the 20th century has unveiled some of the deepest mysteries of the cosmos, and yet again we may be on the verge of discovering the mechanisms that explain in great detail our universe and our place in it. Look at the observable universe, which is the piece of the universe and beyond indeed that we are claiming to understand and are indeed understanding in detail, and you realize that maps like this show you there are 350 billion large galaxies in the observable universe, which is 90 billion light years across, and we claim to understand how all that interacts, what it's made of, and indeed where it came from. And I think the size of our quest, the almost hubristic nature, becomes quite obvious. And the numbers are really quite ridiculous. The universe is big, I suppose, is what I'm trying to say. As well as understanding a map in the size and scale of it, we understand, of course, in detail, in some great detail, the evolution of it from very close to the Big Bang. The fact that we can even talk about numbers like 10 to the minus 43 seconds after the Big Bang is remarkable. Of course, that number comes from the Planck scale, which comes from the weakness of gravity. There are 4 forces that we know of in the universe. Gravity is by far the weakest one of the great mysteries, is why gravity is so weak. So we talk about numbers like that. We then have the beginnings of experimental data when we start to talk about the time period from 10 to the minus 36. To avoid a 10 to the minus 32 seconds, that's the period when we think the universe went through an exponential period of expansion, increased in size by a factor of 10 to the 78, less than the blink of an eye. The reason I say we have experimental data in principle is that certainly the measurements of the cosmic microwave background fit in with that theoretical statement. The idea that that's the way that physics was, there was that exponential expansion back then, certainly not proven by any sense, and the mechanism, of course, is not understood, but the fact that we have a window now with precision cosmology for the first time on those eras is, I find, quite remarkable. In order to fully understand what makes the universe tick, we have to be able to grasp its early stages and the universe's subsequent evolution. The earliest stages of the universe's existence are estimated as taking place 13.8 billion years ago, with an uncertainty of around 21 million years in the very early universe. The subnuclear particles that later made up the protons and neutrons existed in a free state as a quark-Coulomb plasma. As the universe expanded and cooled, the quark-Coulomb plasma would undergo a phase transition and become confined into the protons and neutrons we know and love today. Cosmologists can give us a glimpse of the early universe way before nuclear synthesis begins. Enter the Planck epoch. The Big Bang occurs, in which ordinary space and time develop out of a primeval state. During the Planck epoch, cosmology and physics are assumed to have been dominated by the quantum effects of gravity, but we have yet to develop a theory of quantum gravity in physical cosmology, assuming that nature is described by grand unified theory. The grand unification epoch was the period in the evolution of the early universe following the Planck keyboard, in which the 3 forces of the Standard Model are still unified. According to inflation theory, the inflationary epoch was the period in the evolution of the early universe when the universe underwent an extremely rapid exponential expansion. The rapid expansion increased the linear dimensions of the early universe by a factor of at least 10 to the 26 power. The electro-weak epoch was the period in the evolution of the early universe when the temperature of the universe had fallen enough that the strong force separated from the electro-weak interaction but was high enough for electromagnetism and the weak interaction to remain merged into a single electro-weak interaction above the critical temperature for electro-weak symmetry. Breaking the quark epoch was the period in the evolution of the early universe when the fundamental interactions of gravitation, electromagnetism, the strong interaction, and the weak interaction had taken their present forms, but the temperature of the universe was still too high to allow quarks to bind together to form hadrons. The quark epoch began approximately 10 to the minus 12 seconds after the Big Bang. During the quark epoch, the universe was filled with a dense hot quark-Coulomb plasma containing quarks, leptons, and other antiparticles. The following period, when quarks became confined within hadrons, is known as the hadron epoch. This started 20 microseconds after the Big Bang. The hadron epoch is mostly characterized when quarks are bound into hadrons, and slight matter-antimatter asymmetry from the earlier phases results in an elimination of antibarons. This symmetry breaking is one of the greatest mysteries of the universe and the reason why we exist. What was it that caused that symmetry breaking? When did it happen, and what are the details of that symmetry breaking? But of course then, when you move to 10 to the minus 10 seconds, a billionth of a second after the Big Bang, or So then we're in firm experimental territory that absolutely is the energy range of the LHC. So we have a very firm, I think that's one of those things that when you think about it for a moment, it's quite remarkable that we have experimental data that tells us about the universe, the physics of the universe, as it was less than a billionth of a second after the Big Bang. Then we move on to nucleosynthesis, the fact that we can calculate with high precision the ratios of hydrogen-helium, in particular deuterium-lithium, in the early universe. NASA's James Webb Telescope will use quasars to unlock the secrets of the early universe. Quasars are high-energetic bursts of very bright light from distant and active supermassive black holes that are millions to billions of times the mass of the Sun, typically located at the centers of galaxies. They feed on infalling matter and unleash fantastic torrents of radiation. Among the brightest objects in the universe, the quasar's light outshines that of all the stars in its host galaxy combined, and its jets and winds shape the galaxy in which it resides. Webb will gaze on 6 of the most distant and luminous quasars. It will study the properties of these quasars and their host galaxies and how they are interconnected during the first stages of galaxy evolution in the very early universe. It is fascinating to think how far the boundaries of ignorance have been pushed by physical cosmology. 20th century science was dominated by the discoveries of modern physics. It stands to reason the 21st century will also be triumphant for cosmologists. Even in 1897, the importance of the beginnings of particle physics, the discovery of radioactivity, was recognized. In fact, if you then look back from the point of view of the 1920s, this is an era 20 years part of a scientific lifetime when we get very quickly the radioactivity, we get quantum theory, we get relativity, the foundations of modern physics. And I found another remarkable quote, actually from Ernest Rutherford from Pisces book. It's a wonderful book if you haven't read it, looking back in 1924, so this is really 25 years after the beginnings of modern particle physics. Rutherford wrote the year 1896 marked the beginning of what has been actually termed the heroic age of physical science. Never before in the history of physics has they been witnessed such a period of intense activity when discoveries of fundamental importance have followed one another with such bewildering rapidity that's looking back at that period, the turn of the 20th century, I actually genuinely think, and I wonder whether many of us do, that we're living through the beginnings of such a period. Now the level of precision with which we understand the universe at some level is quite remarkable, but also the number of experimental results now that are beginning to say that there needs to be a real shift in our understanding are also building up one after the other. We've seen of course dark matter, we're looking at things like the hierarchy problem, dark energy, of course all those results seem to point to a revolution in our understanding of the universe because of the experimental data that we are gathering in both cosmology on the larger scales and in particle physics at smallest scales. We have covered a lot in the early stages of the universe's evolution, but we still have a long way to go, including the epoch of neutrino decoupling, the lepton epoch, Big Bang, nuclear synthesis, photon epoch, recombination, the Dark Ages, star and galaxy formation and evolution, reionization, and finally the present time. We will do them justice and cover them extensively in another video. Thanks for watching. Did you like this video? Then show your support by subscribing and ringing the bell to never miss videos like this. Music, you.